Okay, suppose f is mapping the unit disk into the unit disk, and we have that f of 0 is equal to 0. Then we have a bunch of consequences. Firstly, and this is the most important one, f of z is less than equal to mod z for any z inside the disk, and if f of z absolute value equals mod f of z, then f is linear. I.e., f of z is just equal to some complex number of mod 1 times z. Okay. Second consequence. Oh, I should have said for z not equal to 0, because it's certainly true at 0. Second consequence is that f prime of 0 is less than equal to 1, and again, if the absolute value of f prime is equal to 1, then f is linear. Okay, so proof. So we have unit disk being mapped onto the unit disk with the center being sent to the center. Okay. And what this theorem says is that this is an incredibly restrictive condition for these mappings. So that means that, this condition means that whenever we take a mapping, I should emphasize this is into the unit disk, so we just know it's inside the unit disk in the image. We don't claim we're mapping the unit disk onto the unit disk. So whenever we take any ball inside this thing, then the image of this thing, if this thing is radius r, then the image is contained within something of radius less than r. Yeah? For example, can you think of mappings that satisfy these conditions? What mappings satisfy these conditions? So, example, f of z equals z to the n. For sure, the unit disk is mapped to something inside the unit disk, in this case, actually onto the unit disk. Yeah? And it also clearly satisfies these properties, right? Yeah, so if we take anything which has got radius less than r, then its image is something contained in a ball, even with radius even smaller than r. Yeah? Yeah? And the only way if we take a ball of something less, a ball of radius r, and we have a point on it mapped to something which has got distance r away from 0, the only example of that would be as if we just have n equals 1. Yeah? And therefore it's a linear mapping. Yeah? Well, linear mapping is actually just a rotation with mod a equals to 1. All right. So what this thing says is that if we are mapping from the disk inside the disk, or with 0, sent to 0, then it's kind of contracting space at all scales. It's contracting space at all scales. So no matter what radius r you take around 0, it's going to squash down that thing. And that's kind of surprising. Again, it's completely not true if you don't have holomorphic mappings. It's easy to construct things that don't behave like this. This is not a lot of information to have on the hypotheses, but holomorphic mappings are so rigid that this is actually true and not hard to prove. Proof. Let's take the Taylor expansion of f. So take Taylor of f of z. So it's the sum from k equals 0 to infinity, ak z to the k. Since it's holomorphic inside the disk, then this radius convergence is at least up to the disk. Yeah. So this representation is true for not z less than 1. And tell me something we know about this thing straight away. What do we know straight away about the Taylor series? Yeah. And since f of 0 is just a0, which is equal to 0, so actually we have that f of z is equal to the sum as k is equal to 1 to infinity of ak z to the k. Yeah? Which in particular means that we can just factor a z out like this. Z to the k minus 1. Yeah? And then so we can have f of z over z is this thing, the sum from k is equal to 1 to infinity ak z to the k minus 1. Yeah? And again, this will converge inside the unit disk. Yeah? Cool. So we have that this function, f of z over z, is a nicely holomorphic function. Yeah? It's a nicely holomorphic function. Yeah? Cool. All right. Look at this. What nice information do we also know about f of z over z? And it's obvious we're going in that direction because we're trying to prove something like this. So what nice information do we see about f of z over z? I'm going to erase the board, think about it, and think about the cool stuff that we've proved. We have that f of z over z is this thing. It's the sum from k equals 1 to infinity ak z to the k minus 1. And this is true for z inside. Let's write the disk since we've introduced this notation. Yeah? Okay, so easy things to note is that, strictly speaking, f of z over z is not defined at 0, but it's clearly a removable singularity because by this representation for small z, it's very much like this coefficient a1 and it's bounded, therefore it's removable. And we can remove it by sticking in just the value a1 at 0. Yeah? So we can treat this thing just like a holomorphic mapping. Yeah? With representation given by this. Yeah? In fact, this thing is basically for free saying everything I just said. Yeah? Cool. So this guy is a holomorphic mapping. What we want, we want to show that f of z over mod z is less than or equal to 1 all the time. Yeah? Yeah? Yeah. So that's the same as saying that the image of this guy is going to be contained inside the unit ball. Yeah? So this mapping is defined on the disk, and we want to show that its image is contained within the disk as well. Yeah? So let me do this as the disk. We want to show that this is true. Yeah? And I draw it like it's strictly contained. It doesn't, of course, have to be strictly contained, but we do need it to be contained. Yeah? It's really awful the way I wrote that. Let me get rid of that. All right. What tool do we know could help us with this? So here is 0. We want to show that this thing isn't too far out from 0. What tool is useful for that? Generally, if we have a holomorphic mapping, I spelled generally. I think that's just one R. If we have G from some domain into the complex numbers, where do we find Z such that G of Z is the supremum of all of these guys? Is it 0? right? So this is for a general. This is just for a general holomorphic mapping, mapping some region into the complex plane. Yeah. So it's mapped onto this thing. Yeah. So where are we going to find the z that maximizes the distance away from 0? So suppose 0 is here. So there is some definite distance here that maximizes away from 0. Yeah? Because it's holomorphic, it's continuous, the image is a bounded thing if our original thing is bounded. Yeah? So where do we find it? Could z0 be here? On the boundary, right? Tell me why it can't be in the interior. Why can't we have z0 be somewhere here and then this thing here is g of z0? Why is that impossible? Why is that impossible? Give you a hint. Let's draw a little ball around here. The open mapping theorem. Yeah. So the image has to be an open set, right? Yeah. Yeah. Has to be an open set. Yeah. So we can't have that this guy is on the boundary because then there would be some little open neighborhood around it where we could make it a little bit bigger, right? Yeah. So indeed, there is no z0 inside our domain that maximizes this. It has to occur on the boundary somewhere. Okay, cool. Right, so why is that useful in this thing here? We're trying to show that the image of this thing is contained inside the disk. Yeah? Yeah? And what we have to really care about is what happens to this thing near the boundary. Yeah? On the boundary. So let's take some r between 0 and 1 with r very near 1. Okay? So then consider this thing. Consider f of z over z on Vr of 0. Let's consider this thing. Yeah? And we know that if we try to find the guy mapping the smaller Br of 0, we're trying to find the guy that is taking it furthest away from 0, that thing has to be achieved on the boundary somewhere. Yeah? Has to be achieved on the boundary somewhere. Yeah? So take z0 such that f of z0 over z0 is equal to the supremum over the ball of radius r around 0 of this stuff. Yeah? Yeah? Cool. All right, so by maximum principle, z0 hold on. We do. Thank you, yes. This thing has to belong to the boundary around 0. Yeah? And why is that cool? Why is that useful for us? Look at this expression here. This expression. This is a hint. Yeah? Now what? Yeah? And why does that make me happy? What can I do from here? What bound do I have now? Say it louder. Well, before we do that, tell me what bound I have. I want to make some explicit bound, right? I want to put some explicit bound. What explicit bound do I have from here? If I have any, do I have anything here I can put? What information do we have from the hypotheses? So the hypothesis was that f of 0 is 0, and the hypothesis was that, yeah, the mod of f of z is never bounded by 1. Yeah? Jaime's doing a lot of the answering. Let's other people get involved. Huh? I want you all to give me your feedback. Okay. Cool. All right. So this is some explicit bound for our function, but not quite in the entire disk, in something a bit smaller. Yeah? Yeah? Because this guy has to be achieved on the boundary, and on the boundary we have this thing. Yeah? So the supremum over the ball of radius r around 0 of our thing is less than 1 over r. And we're taking r to be very close to 1. Yeah? So it's not quite what we want, but very nearly, right? Very nearly. Yeah? So we've shown that if we are slightly inside with this ball of radius r, yeah, then this expression we're trying to control, f of z over z, is bounded by 1 over r. Yeah? Yeah? And r is a bit less than 1, so this is a bit bigger than 1. But the natural thing now is just to let r tend to 1, and then that will give us exactly what we want, right? So letting r tend to 1, this gives us the supremum, this thing. Why did I have to do this stuff with the taking some r a bit less than 1? Why did I bother with this? Why couldn't I have just directly done this on a ball of radius 1? Perfect. F is not defined outside of the ball, right? So there's no meaning to picking some specific value on the boundary. It just doesn't mean anything. Yeah? The actual statement of the maximum principle is that the maximum is not achieved on the interior if you happen to have something which is also defined in the boundary. Therefore, corollary it's achieved on the boundary, the maximum. Yeah? Cool. So I now have this. Now let's backward engineer what would happen if we actually had an equality. Right? If we actually had an equality. Yeah? So suppose for some, I should have probably said that better, z0 inside this unit disk, we have that f of z0 over z0 absolute value is equal to 1. Yeah? That would contradict the maximum principle unless, so the maximum principle followed from the open mapping theorem, which is true unless open mapping theorem says that the image under a holomorphic map, unless it's a constant, right? Because a constant function is a perfectly good holomorphic mapping, but its image is just an individual point, right? Which is clearly not open, right? So the open mapping theorem is for a non-trivial holomorphic mapping. The maximum principle is for a non-trivial holomorphic mapping. And if you have something that contradicts it, you know, then that thing has to just be just a constant mapping, right? Yeah. So then by maximum principle, we have that this mapping f of z over z is just a constant, all z, and by this thing, the constant is just got norm 1, i.e. f of z is equal to c times z. It's a linear mapping with a coefficient of norm 1. In other words, just a rotation. It's just a rotation. Yeah? Cool. All right. So that is almost the full statement. Final. We need to establish that f prime of 0 is less than or equal to 1, and if f prime of 0 equals 1, then f of z is equal to c times z mod c is equal to 1. All right, so help me with that. How can we show that? Yep. Perfect. Yep. And since f of 0 is 0, right? Then this is equal to the limit, the limit as z goes to 0 of just f of z over z, and we've already established that this thing is less than or equal to 1, right? So just by the fact that this is a holomorphic thing and therefore it's continuous, right? So f of 0, the absolute value is a continuous function, right? Is this thing, the limit as z goes to 0, f of z over z, which is less than or equal, which is equal to the limit as z goes to 0 of this thing, because absolute value is continuous, and this is a continuous function, so this thing is just less than or equal to 1. I actually don't even need that, I just need that this is less than or equal to 1. So we're all good. Yeah? Cool. So that's definitely true. And if we have that, this thing is equal to 1, then that would mean that the absolute value of the limit as z goes to 0 of f of z over z is equal to 1, right? But f of z over z is a holomorphic function, right? And it has some value at 0, yeah? And that value would therefore be equal to 1. Its absolute value would be equal to 1, right? Yeah? So f of z over z at z equals 1, sorry, z equals 0, if I said 1 I meant 0, is such that has absolute value equal to 1, right? Yeah? Which again contradicts the maximum principle unless it's constant. Because again, f of z over z, even though I can't easily stick in the value 0 into this, it is a holomorphic function because we've seen the singularity at 0 is removable. Which max principle. Unless f of z over z is just equal to a constant and mod c is equal to 1, and we have exactly what we need. Yeah?